3.3 through 3.7. Though looking through it, you can see that we're kind of skipping around. Really what we're going to be doing today is we're going to be learning all of the differentiation formulas. And so last time we introduced the idea of what the derivative is and how we can calculate it. Basically, it's this formula. The derivative of a function f of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And that's the difference quotient definition of derivative. It is not very practical to do this for most functions, though. And that's why we have a number of shortcuts. And today's lesson is going to be to teach you all of the shortcuts so that you can take the derivative of any function that you are given. Here is the example. Imagine using the difference quotients to calculate d dx of the natural log of the absolute value of x times cosine of 2 to the tangent of square root of x. That is a horrible, horrible function. And if you want, this is what the graph of it looks like. I actually graphed it real quick because I was curious. And as you can see, it starts out going off to negative infinity down here. And then it comes up and it just becomes static right here. And then as it continues, it repeats. And you get all of this odd behavior where it goes from a high point down to a low point before it starts oscillating an infinite amount, and then it starts back at a high point. What the derivative would represent is it would represent the rate of change or the slope of this curve at every single point. And we should be able to calculate this without too much trouble. I actually have the answer a little bit lower on this page, but with this problem, I haven't done it in about a year and a half or so, and it's always fun to see if I still have the chops. And so let's stop the share real quick, and let's see if I can find the derivative of this by hand before we actually do our lesson. And so the derivative of the natural log of x cosine of 2 to the tangent of square root of x is going to be equal to 1 over x cosine of 2 to the tangent of square root of x. And then that is going to be plus, let's see, a natural log of absolute value of x, a sine, and let's actually change this to a minus of 2 to the tangent of square root of x. Then we'll multiply that by a natural log of 2 times 2 to the tangent of square root of x. And then we will multiply that by, how about secant squared of square root of x. And then let's divide this entire thing by 2 square root of x. And so my claim is that this is the derivative. And let's see if I was correct or not. Share the screen. And so scrolling down, we have the 1 over x. I did it as an over x here, it looks like. Cosine of 2 to the tangent root x minus, got the sign right, natural log of x, sine of 2 to the tangent root x, ln of 2, 2 to the tangent of root x, secant squared of root x, and over 2 root x. Cool. And so I haven't done this problem in a year and a half, 2 years, and I'm still able to do it without too much trouble. By the end of today, the goal is for you to be able to do that computation in about that same amount of time. And that's really the main goal. We want to make sure that you know all of the differentiation tricks so that you will be able to take the derivative of anything in seconds. I put this in under a minute. I think it probably took me just a little bit under a minute to get that one all written out. And really, it becomes an issue of just writing out the answers. Because notice, when I did this problem, there was no work to show. I actually just took this function. I broke it down into all of its different components. In this case, we had the product of two things. And then we had a composition of a number of functions. And then I just used the differentiation rules, which we'll soon be discussing, to figure out exactly what the derivative is. And so let's make sure that we know our differentiation rules. We'll start with the easy one, the constant rule. So suppose that you want to take the derivative of a constant function. And so f of x equals k, where k is 5 or 2 or 7 or just some number. Well, remember that the derivative just represents the slope of the function. If the function is a constant function, then the slope is always 0. And so you're going to get a derivative of 0. If you want, you can check it using the formal definition. And here it is using the difference quotient definition. The derivative of f of x is equal to limit as h goes to 0 of f of x plus h minus f of x over h. But both of those would just be k. And so k minus k over h is 0 over h, which is just 0. So the constant rule, derivative of any number is just 0. And so the derivative of 5 is 0. The derivative with respect to t of negative pi to the e is also 0, because negative pi to the e is just a number. That's not too bad. Next one's a little bit trickier. And so suppose that you want to take the derivative of a variable with an exponent n. And so x to the n. This is called the power rule. We've done some of these in various forms. The derivative of x is 1 because the slope of x is just 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. If you notice, there's kind of a pattern going on here. That pattern is whatever the exponent is, it's coming down to the front, and then we're subtracting that exponent by 1. And it turns out that is always going to be the case. And so for the power rule, you're always just going to be bringing that exponent down to the front, and then you're going to be subtracting the exponent by 1. If you want, here's the proof using Pascal's triangle, but here's the formal one. And so if f of x is equal to x to the n, then f prime of x is equal to n times x to the n minus 1. Now, here's the thing. This proof that's right here, this is only really for integer values or natural number valued exponents. But the cool thing is this will work no matter what n is. Even if it's negative or a fraction or an irrational number, this rule still works. And here's some examples. And let's try these examples real quick. So d dx, try them on your own real quick, and then we'll do them together. d dt of t to the 7th, d dx of 1 over x to the 5th, and d dt of the cube root of t squared. And so the first one, d dx of x to the 19th. Our power rule says that we can just bring that exponent down and subtract our exponent by 1. And so the derivative of x to the 19th is 19x to the 18th. With this one, derivative with respect to t of t to the 7th would be 7t to the 6th. With this one, be careful. You have to remember how negative and fractional exponents work. And so d dx of 1 over x to the 5th is really d dx of x to the negative 5. And so you would bring that negative 5 down, and then you would subtract it by 1, which would give you a negative 6. And so you would get negative 5 over x to the 6th. Same with this one. And so we can rewrite this as d dt of t to the 2/3. We can bring that 2/3 down. And then our new fractional exponent would be 2/3 minus 1, which would be a negative 1/3. And we could rewrite that in radical form and rationalize it if we really wanted to. Oftentimes you'll just keep it like this because it can get very, very messy. And that's our power rule. The next rule is the scalar multiple rule. And this is one which is very easy to get mixed up with the constant rule. I think in the notes online, I might actually have it written as the constant rule down here. And so I made sure to edit it for these notes. The difference between a constant and a scalar is a constant is just a number which is alone. And so if we were to have something like y equals 7, this would be a constant. If we had y is equal to 7x squared, this 7 would be considered a scalar because it's being multiplied by some other function. Really what this is doing is this is taking 7 and it's taking the x squared and it's stretching it by a factor of 7. And so the slope would be multiplied by a factor of 7. And that actually comes into how we can use our scalar multiple rule. And so whenever we have a scalar, a number which is multiplied by a function, when we take the derivative, that number is just going to stay there. And so when we take the derivative of k f of x, we get k f prime of x. And if you want, here is the proof for it. And so whenever you have a number like 7x to the 5th, or the 7 in 7x to the 5th, that 7 is just going to hang out. And so I will do the first two examples here. ddx of 7x to the 5th and ddy of 3 over y. And so for this first one, we bring the 5 down, and 7 times 5 would give you 35. We subtract the exponent by 1, giving 4. For this one, we remember that a y in the denominator would be the same as y to the negative 1. Bringing the exponent down, we get negative 3, y to the negative 2. And if you wanted to, you could clean that up, make it negative 3 over y squared. And so that's our scalar rule. So far, we've got the constant, the power, and the scalar. Now we've got our sum and difference rules. Sums and differences actually work very nicely. And so suppose that you want to take the derivative of the sum or difference of two functions. And so let's say you have f of x equals u of x plus v of x. Well, if you want to take the derivative of f of x, really you can just take the derivative of u of x and v of x separately, and you're done. It's easy to prove. If you want, you can prove it on your own. But if you're ever taking the derivative of the sum of two functions, you can just take the derivative of the two functions separately. And if you want, here is a couple examples. Let's just do the first one. ddx of 5x squared minus square root of x. Notice I put it in parentheses. Technically, this derivative is applying to everything. And so it's a function transformation, and you would want to make sure that you're showing that it's applying to everything in there. Looking at this, the derivative of 5x squared is 10x, or 10x to the first. The derivative of the square root of x, well, remember that would be square root of x is x to the 1/2. And so you would bring the 1/2 down and then divide, and then subtract 1. And so let's say y is equal to this, then y prime would be equal to 1/2 x to the negative 1/2. But that ends up just being 1 over 2 square root of x. I actually just kind of memorized this one because you see the derivative of the square root pop up a lot. And that's actually one that I used when I was doing that first problem, the really long one. So this would be 1 over 2 square root of x. Much better than doing the difference quotient, right? Ooh, the next one, derivative of exponential functions. And so we've talked about the number e in the past and said it's an irrational number, which is roughly 2.7182818459045. What's interesting about this number e is that it has a very specific calculus definition. And it's tied to this idea here. And so think of the function a to the x, where a is just any number. The difference quotient definition would give us this. So d dx of a to the x is equal to the limit as h goes to 0 of a to the x plus h minus a to the x over h, which is equal to the limit as h goes to 0 of a to the x times a to the h minus 1 over h. What's interesting about this is we started with a to the x and we ended with a to the x times this limit right here. And depending on what your a value is, this will approach different numbers. However, if this a number were e, the number e, 2.7-ish, then this limit would go to 1. And that's how we define e. E is the number such that this limit is equal to 1. And that makes it so that the derivative of e to the x is e to the x times 1, which is just e to the x. E to the x is a function which is its own derivative. And that's why e to the x is so special. Once you start playing with differential equations, you'll see that e to the x is almost always tied to the solution because it's kind of the base case for when something is its own slope. And so everything is done in terms of e to the x. Here's a couple of practice problems. The derivative of e to the x, don't overthink that one. It is e to the x. ddt of 7e to the t plus 3. Well, the derivative of 7e to the t would be 7e to the t. And the derivative of 3 would just be 0. And so the answer would be 7e to the t. Ooh, sine and cosine are a little bit more interesting. And so this is really where you get to test your knowledge of trigonometry. Here are the formal proofs for them. And so let's just look at the sine one. The derivative of a sine, if we use our difference quotient definition of derivative, would give us sine of x plus h minus sine of x over h. But sine of x plus h is a sum on the inside, right? And so we can use our sum and difference formulas from trigonometry. So sine of x plus h would be equal to sine of x cosine h plus sine of h cosine of x. Now notice, looking at this, we have a sine of x term here and a sine of x term here. We can factor those two, or group those two terms together, giving us limit as h goes to 0 of sine of x times cosine of h minus 1 over cosine of h, plus the limit as h goes to 0 of cosine of x times sine of h over h. Well, this limit here, cosine of h minus 1 over h as h goes to 0, is something we can calculate. And it turns out it goes to 0. And so this term right here goes away. And this one, sine of h over h as h goes to 0, that was the one you're supposed to memorize. That goes to 1, which means the derivative of sine of x is cosine of x. Similarly, the derivative of cosine of x is actually negative sine of x. And so sine goes to cosine, cosine goes to negative sine. They just kind of go back and forth between one another. If you take the derivative 4 times, you're back to your starting function. And so here's a couple of quick examples. The derivative of 5 sine of x would be 5 cosine of x. The derivative of cosine of t plus 3 would be negative sine of t, because the derivative of cosine is negative sine, and the derivative of 3 goes to 0. I think we're getting to the product rule. Oh, we are. So now we're getting to one of the bigger ones. There are 3 really big rules: the product rule, the quotient rule, and the chain rule. And the product rule is the first big one. Suppose that you have the product of 2 functions. And so f of x equals u of x times v of x. Well, we can't just take the derivative of each and keep it as a product. That's unfortunate. It'd be very nice if we could, but it does not work that way. And we can actually do the difference quotient definition on this function and see what happens. And that's what I've got worked out here. Derivative of u times v is equal to the limit as h goes to 0 of u of x plus h, v of x plus h, minus u of x, v of x over h. If we get creative, we can insert a new term by subtracting it from the first term and adding it to the second term. And when we do that, we get this interesting relationship, which leads to this solution. The derivative of u of x, v of x is equal to u times v prime minus u prime times v. The order for the product rule does not matter. The order for the quotient rule, which is going to be the next big rule, does matter. And so with this one, as long as you were taking the derivative of one of them and multiplying it by the other, and then you're taking the derivative of the other and multiplying it to the one, you're going to get the exact same answer. And so you can do it as u v prime plus u prime v, or you can do it as u prime v plus u v prime. Either way works. Let's see what this looks like. And so let's write these two examples down. d dx of x squared e to the x and d dt. I'm going to make that one a little bit more interesting. Let's say t to the 27th cosine of t. And so looking at this first one, if it helps, you can underline stuff. And so we would say this is our u, and this is our v. Then what we're going to get when we take the derivative of this is going to be u, or I guess let's do u prime times v plus u times v prime. That's the order I usually do things. And so start with the derivative of x squared, which is 2x. And then we have v just in its raw form. We're not taking the derivative of it at this point. Plus u, which is just x squared, times v prime. The derivative of e to the x is just e to the x. And so this is our derivative. Same with this one. And so looking at this one, derivative of t to the 27th cosine of t. Well, the derivative of t to the 27th would be 27t to the 26th times cosine of t plus, and then it's going to be t to the 27th. And the derivative of cosine would be negative sine. The way I usually write that is I'll put the sign here, and then I'll put the minus sign over here. You really wouldn't want to put the minus in between the t to the 27th and the sign, because then it might look like you're subtracting them. And so moving the minus sign to the front makes it a little nicer. And if you want, you can double check. And so again, this is our u, this is our v. And we ended up getting u prime times v plus u times v prime. That is our product rule. And again, for the product rule, the order does not matter as long as you're doing a derivative times a non-derivative, and then a derivative times a non-derivative. For the quotient rule, though, which is the next one, the order very much does matter. And so notice with this one, we have u of x and we have v of x. U of x is the top function, v of x is the bottom function. And when we do this calculation, it's very similar to how we broke down the other one. The derivative of u over v is v times u prime minus u times v prime over v squared. because there is this minus sign in there, the order very much matters. And so we have this formula for it. If f of x is u over v, then f prime is v times u prime minus u times v prime over v squared. Now, when I was in college, I could not memorize it for the life of me throughout Calculus 1. I just could not memorize it. Then my Calculus 2 instructor gave me a way to remember it, and it was a limerick, which made it much, much easier to remember. And it's the hi-ho rule. And so since it's hard to remember, instead of using the u's and v's to remember the order, you can use this idea of the derivative of hi over ho. Because the derivative of hi over ho becomes ho d hi minus hi d ho over ho ho. And that's hard to forget because there's a hi d ho, and the hi d ho is always at the end. And so it's the second component in the numerator. And then the ho ho is the value squared in the bottom. Once they showed me this, I never forgot it. You also see it sometimes as the derivative of high over low, and then it's low d high minus high d low over ho ho. And this d high would represent the derivative of the high component, the derivative of the numerator. The d ho represents the derivative of the denominator. And so let's see if we can do these calculations. Neither one of these is that good because the e to the x, the derivative of e to the x is just e to the x. And so let's do one that's a little different. Let's say that I want to find the derivative of x to the 15th over sine of x. There we go. So the derivative of x to the 15th over sine of x. Well, in order to calculate this, we would say ho d high, and so it's going to be the sine of x times the derivative of the numerator. So the derivative of the numerator would be 15x to the 14th minus high d ho. That's going to give us an x to the 15th times the derivative of the bottom, which is cosine of x, over ho ho, which is the bottom squared. Sine squared of x. The quotient rule, you're almost always going to get a very messy solution. Notice this is not a very nice looking answer, and frequently you won't be expected to simplify it. Sometimes if it's simple polynomials, you may be asked to simplify and reduce, but oftentimes your answer will just look this messy. Let's do another example. How about d dx of square root of x plus e to the x over x plus cosine of x. This should be just gross because we have a sum in the numerator and a sum in the denominator. But it's just going to be applying the same formulas. And so it is ho d high, which is x plus cosine of x, times the derivative of the top would be 1 over 2 root x plus e to the x. And notice I put everything in parentheses here. That is very important. If you forget your parentheses, then you'd only be multiplying the cosine by this term, and both of these need to be multiplied. Remember how FOIL works. Minus high d ho. So our high would be square root of x plus e to the x. D ho, the derivative of the denominator, would be 1 minus sine of x over ho ho. And that is the formula for the derivative of this function. Now, if you want to really challenge yourself, try and do this using the difference quotient definition. And I'll give you a minute to try that. and then I'll tell you don't do it. So I hope that some people actually pause the videos and try to do that, because you would have a nightmare of a time doing that. Yeah, no, definitely using these formulas, these tricks, is going to be the way to find the derivative of most things. That's the quotient rule. Now that we have the quotient rule, we can figure out all of the other trigonometric functions. And so we know that tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine. Let's just try and determine what the derivative of tangent is real quick. So to determine what the derivative of tangent is, we will treat it as sine over cosine. And so ddx of tangent of x is equal to the derivative of sine of x over cosine of x. Well, using our quotient rule, it's Hody high, so that's going to be cosine of x times the derivative of sine of x is cosine of x minus Heidi ho, high, the derivative of cosine would be a negative sine. So it'll be a sine, and then we'll bring the sign out, the negative, over ho-ho, cosine squared of x. Well, this gives cosine squared plus sine squared in the numerator. And cosine squared plus sine squared is 1. That's our trig identity, the Pythagorean identity from back in trig. And so we get 1 over cosine squared of x, but 1 over cosine, we have an identity for that also. 1 over cosine is secant. And so we get the derivative of tangent is secant squared. Turns out all of the trig functions have something similar. And so the derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant tangent, and the derivative of cosecant is negative cosecant cotangent. Once we have those, we can plug them into a number of different scenarios. Let's just create something new. These aren't that particularly interesting. And so let's suppose that we want to find the derivative of, how about x squared secant of x? We'll notice that this is the product of two things. And so we would use the product rule. The derivative of x squared is 2x. And then the secant of x hangs out, plus the x squared hangs out. And then we need the derivative of secant. And the derivative of secant is secant tangent. There we go. One more. How about the derivative of, let's do secant. If we just did secant, let's try a different one. How about cosecant? Cosecant of x minus e to the x over x to the 7th, and then let's do a plus cotangent of x. This will be gross. This will be very gross, and we'll probably fill up the rest of my whiteboard because this is a quotient rule. And so the quotient rule, we would say it's Hody high. So it's going to be x to the 7th plus cotangent of x times the derivative of the numerator. The derivative of cosecant is going to be negative cosecant cotangent. And the derivative of negative e to the x is negative e to the x. Minus Heidi ho. And so the top just stays the same. And the derivative of the denominator is going to be 7x to the 6th plus the derivative of cotangent would give us a negative cosecant squared. All over, ho-ho, x to the 7th plus cotangent of x squared. That is the formula for the derivative of this function. And so you can see how these things can get a little bit tedious and complicated, but they're not difficult because there's no actual work to show. All of these are single-step problems. We start with the problem and then we get the solution immediately. Ooh, now we're up to the hard rule, the chain rule. So we've done sums and differences, we've done products and quotients. The main operation we're missing is compositions. How do you take the derivative of a composition of a function? And there's a proof here. The proof is not nearly as nice as you might want it to be. And honestly, I would recommend focusing more on how to actually do these computations than the proof for the chain rule. The way the chain rule works is if you have a function inside of a function, basically you work your way out. And so you would start by saying if f of x is equal to f of g of x, then f prime of x is going to be equal to f prime. And so the derivative of the main function, still with the inside function on the inside. And then you multiply that by the derivative of the inside function. The way you sometimes written or see this written, and I write the physicists, also known as cheaters, use Leibniz's notation to write this. Because when you write it in Leibniz notation, you see df dx is equal to df du dx. And you can kind of just say, oh, the du's cancel, and it's clear that it's all true. But oftentimes when you do that, you might make some small mistake. And so let's see if we can actually see what this looks like in practice. I have a couple examples down there. Let's start with an easier one. Let's say that we want to take the derivative of sine of x squared. Notice that this is the composition of functions. We have an outside function and we have an inside function. The way that we use the chain rule is we start by taking the derivative of the outside function. So the derivative of sine is cosine. But this is not going to be cosine of x. Instead, this is going to be the cosine of x squared. This stuff that's on the inside, it stays on the inside. And then we multiply by the derivative of the inside bit. So the derivative of x squared is 2x. So notice when we did this, we have our main function and then we have our interior function. Well, this is the derivative of the main function, and this is the derivative of the interior function. And we're just multiplying them together. Let's do another example. How about d dx of tangent of sine of x plus e to the x? And so again, this has a main function and then an interior function. The interior function is actually comprised of the sum of two functions. When we take the derivative of this, we start with the outside. And so the derivative of tangent is going to be secant squared. And usually the way I think about this is I would say, this is the derivative of tangent of stuff. And the derivative of tangent of stuff is secant squared of stuff. That stuff hasn't changed. But then we need to multiply by the derivative of that stuff. And so the derivative of sine of x plus e to the x, well, the derivative of sine of x is cosine of x, and the derivative of e to the x is e to the x. So we had the derivative of tangent of stuff, which was secant squared of stuff. And then we had the derivative of sine of x plus e to the x, which was cosine of x plus e to the x. That's our chain rule. But these are relatively simple examples of the chain rule. The reason it's called the chain rule is because we can chain this together as many times as we need to. And so let's suppose that we have something that looks like this. The derivative of how about the square root of tangent of e to the x minus the sine of x squared. Give this one a shot, and then we'll compare. And now that you've given that one a shot by pausing the video, we have our core function, which is the square root. We then have a tangent function inside of that. We then have the e to the x minus sine of x squared, which has an e to the x component, and then the difference with the sine of x squared, where the x squared is inside of that sine function. And so we are just going to unravel this like an onion. We will start with the derivative of the square root of stuff. And so the derivative of the square root of stuff, if you remember from earlier, is going to be equal to 1 over 2 times the square root of that stuff. And so this is going to be 1 over 2 square root of tangent of e to the x minus sine of x squared. Now we multiply by the derivative of that interior stuff. And so the derivative of tangent is secant squared of stuff. Now that interior bit was the difference of two things. The first bit was e to the x, and the derivative of e to the x is e to the x. The other one is sine of x squared, which is again a function inside of a function. The derivative of sine of stuff is cosine of stuff. And the derivative of x squared is 2x. And so this is the derivative of this function. And we just chained it along. We started with the derivative of the square root, then the derivative of the tangent, and then the derivative of the interior components. But our interior components had the e to the x, and then it also had the sine of x squared, which itself had two parts. This is where understanding the structure of functions really comes into play, because now we're dealing with compositions, sums and differences, as well as products and quotients. And depending on the order that you have, you're going to be able to do all of these different operations to calculate the derivative. Let's do one more. This time, let's do a product. So let's say that we have the derivative of, how about e to the sine of x times tangent of, how about, I'll go with square root of x again. I like square root of x. And so again, we want to try and understand the structure of this function so that we can find the derivative of it. This is the product of two functions, which means that we're going to be using the product rule. But within each of these, we have a chain, because we have a function inside of a function. We have a function inside of a function. And so we are going to be using the chain rule and the product rule at the same time. And so let's start with our product rule. The derivative of e to the sine of x. Well, the derivative of e to the stuff is e to the stuff. And the derivative of that stuff, derivative of sine, is cosine of x times our tangent. We then keep our e to the sine of x. And then we need to multiply that by the derivative of tangent of square root of x. Well, the derivative of tangent of stuff is secant squared of stuff. And then we need to multiply that by the derivative of that stuff. If we think of this in terms of u and v, what we've done is we've said that this is our u prime times v, and this is our u times v prime. However, notice that u prime is itself a chain rule, and our v prime was also a chain rule. And so that's the chain rule. Chain rule, there's a lot to it, especially when you start mixing and matching chain rule with all of the other rules that we are playing with. But the chain rule also gives us the last tool we need to figure out the last of the formal formulas, I guess. The rest of the derivative formulas. And so remember our derivatives of exponential functions where we figured out that the derivative of e to the x is e to the x? Well, we can use that and the chain rule to figure out all of the other derivatives for a to the x when a is not e. And so if we wanted to find the derivative of 2 to the x, well, it turns out 2 to the x would be e to the x natural log of 2. That's how we could define it if we wanted to. That's one of the rules of exponents. Well, using that, we could say that the derivative of a to the x is the derivative of e to the x ln a. Well, the derivative of that, use the chain rule, you'll get a natural log of a that comes out. And you'll get the natural log of a times a to the x. And so for anything which is not a e to the x, we're always going to get a natural log term that comes out as well. Those actually look pretty good. And so let's do those. d dx of 2 to the x. And then we will do d dx of pi to the cosine of t. And so the derivative of 2 to the x is going to be giving us the natural log of 2 times 2 to the x. The derivative of pi to the cosine of t, well, now notice this is a chain rule. Derivative of pi to the stuff is natural log of pi times pi to the stuff. And the derivative of that stuff, oh, this was a ddt, sorry about that. Derivative of cosine would be a negative sine of t. And so there that one is. This exponent rule or exponential rule, it often messes folks up because when we think about it, we have a different rule for this function, d dx of, let's say, 19 to the x, as opposed to d dx of x to the 19th. The derivative of 19 to the x is going to be equal to the natural log of 19 times 19 to the x. Whereas this one just requires the power rule, 19x to the 18th. The key difference is where the exponent is. If the exponent is in the base, then it's a polynomial, and we can just use the power rule. If the exponent, or if the variable is in the exponent, then it's an exponential, which means we have to use our exponential rules. If we have exponents, The last one is logarithms. I think that's the last one. Yeah, that's the last one. Logarithms, again, it can get pretty messy to prove it. I have the proof written here if you'd like. But the crux is that it's actually fairly nice. The derivative of the natural log of the absolute value of x is equal to 1 over x. You do not necessarily have to have that absolute value in there. It'll still be true. So the derivative of natural log of x is 1 over x. The derivative of natural log of absolute value of x is equal to 1 over x. The key difference between the two is what the domain is. The domain of natural log of absolute value of x is all real numbers except for 0. If we did not have the absolute value, it would just be a domain of positive real numbers. In either case, though, the slope is just going to be 1 over x. We can also use the change of base formula to show that if you're dealing with any other logarithm, you're just going to be dividing by whatever that base is. And so we get these two formulas. The derivative of natural log of x is 1 over x. And the derivative of log base a of x is equal to 1 over x ln a. And these two problems look pretty good. Let's try them. ddx of x ln x and ddx, or sorry, ddt of log base 3 of sine of t. And so looking at this first one, it is a product because this is the product of two functions, which means we need to use our product rule. Using the product rule, the derivative of x is 1 times natural log of x plus x times the derivative of natural log. The derivative of natural log, we just stated, is 1 over x. And so we actually get the derivative of x ln of x is just equal to the natural log of x plus 1. That one's kind of fun. You can actually use this later on to do the antiderivative of natural log, but we'll save that for another day. For this one, log base 3 of sine of t, notice that this is a chain. This is the composition of two functions. So we start with the derivative of log base 3 of stuff. And well, log base 3 of stuff is going to have a derivative which is equal to 1 over the natural log of 3 times that stuff. And then we need to multiply by the derivative of that stuff. Derivative of sine is cosine. You could move this to the numerator. You could actually rewrite cosine over sine as cotangent. We got options there, but that's the answer. Then let's see, where's my share screen? There's my share screen. And that gives us our formulas. And so far we've covered a ton of formulas. Looking through, we did all of them. We skipped the absolute value one because that one's kind of silly, but we did all of them up to about here. And so the constant, scalar, sum and difference, product, quotient, chain, power, the exponential functions, the logarithmic functions, and the trigonometric functions. Knowing those will get you very, very far. And as far as this course is concerned, that should be sufficient to understand all of the derivative problems that you'll be seeing in the homework. There are other differentiation formulas, though, because there are other functions. If you remember from trigonometry, we also have the inverse trig functions. And that would be these. And we have formulas for those. We also have the hyperbolic trig functions, which you may or may not have seen. They're really an extension of exponentials. But we have the hyperbolic trig functions and the inverse hyperbolic trig functions, which you can derive if you want to. For the purposes of this course, Math 355, You do not need to have those memorized. All of these through the trigonometric functions, except for the absolute value one, which you don't need, these you need to know. And you need to know them like the back of your hand. You need to be able to find the derivative of anything using these functions. And it can be any composition, any product, any sum or difference. You can make a function as gross as you want. You need to be able to solve it. These down here, if you were taking Math 400, you would need to know them. But we're not Math 400. We're an accelerated course for biology and medicine. And part of that acceleration comes from cutting the number of functions we have to do in half. And so that should hopefully help. And realistically, these are the functions which are going to be the most important for you. Having the polynomials, the exponential and logarithmic, and the trigonometric functions, those get you very, very far. And in fact, the inverse trig, hyperbolic trig, and inverse hyperbolic are really just extensions of those functions which we already have. And so make sure that you have these functions and you'll be in good shape. That said, the last thing here is just let's take the derivative of everything. And you should be able to take the derivative of anything and everything. There are a number of practice problems here. If you want to do any of them, send me an email. I don't really want to go through the entire laundry list. Oftentimes when we'd be meeting in person, I would spend maybe a full week just doing random differentiation problems just to get the practice and get students up to the board to do the practice that way. For us, we're just going to end with this last problem here. Natural log of x cosine of 2 to the tangent of square root of x. And let's go back up because I believe that was our first problem of the day. Let's see if we can calculate this one. And I'll give you a moment. See if you can figure out what the derivative of this function is and do it based off of the definitions and formulas that we just developed. Try to find the derivative of that. I will write it down. Then we'll go through it together one last time. Hopefully you paused and tried it. So in order to do this one, first thing we would want to do is dissect the structure of this function. We have a natural log, we have a cosine, and so we have a product of two functions. But this function is a composition, and it's a composition of multiple functions. We have a cosine function, we have an exponential function, we have a tangent function, and we have a square root function. And so this one's going to be a gross chain rule. We start with product though. And so the derivative of the natural log function is 1 over x times this one. And so cosine of 2 to the tangent of square root of x plus derivative of cosine of stuff is negative sine of stuff. So we'll change that to a minus sine of stuff. The derivative of 2 to the stuff is going to be equal to the natural log of 2 times 2 to the stuff. The derivative of tangent of stuff is secant squared of stuff. And the derivative of the square root is going to be equal to 1 over 2 root x. And so we could even just divide this whole thing by 2 root x. Oh, and I forgot something, our natural log. That would have been bad. And so let's throw a natural log of x in at the end. For those who missed where that natural log came from, recall that we are doing the product rule. And so if this is u and this is v, we have u prime times v. And then I would have preferred to have the natural log in the front, but it does not matter the order for the product rule. This is our v prime, and that is our u. Always double check things. So it would have been bad if I'd gotten it wrong in the very last step. And again, double check, make sure that our answer is correct. So when we go to check, we have the cosine of 2 to the tangent root x over x, the 1 over x there. We have the minus sign from the sine term. We have the natural log of x. Oh, I should have put absolute values in there. So natural log of absolute value of x. That modifies the domain and range. It would not actually matter for this function because the square root of x is already basically forcing the function to only be defined for positive values. And so without the absolute value, it should be okay. But we get natural log absolute value of x, we get the sine, we get the natural log of 2 to the stuff, we get the secant squared of stuff, and then we get the 2 root x. And so that's today's lesson. We have learned how to quickly calculate all of the differentiation formulas. And so you should be able to go out and take the derivative of any function that you need to. I would recommend practicing until it hurts. Just practice, practice, practice. You cannot get too much practice for this stuff because this is going to be kind of what defines the rest of the semester. The rest of the semester is going to be focusing on the idea of differentiation and then anti-differentiation, which is where we do the derivative formulas backwards. The idea being, what if I gave you this formula here and told you to find the function which has that as its derivative? So given this function, find this function. That's much, much harder. And you won't be able to do that unless you feel comfortable going in this direction first. And so practice, practice, practice until it hurts your differentiation formulas. And on that note, I think we will call it a day. You have a bunch of homework, but make sure that you get as much practice differentiating things as you can. And remember, you can always go to Desmos to check your answer because it'll graph derivatives for you. You can also use Wolfram Alpha. Wolfram Alpha is a great resource to find the derivatives of things. Just be aware that it struggles with logarithms. It recognizes the common log as the natural log, and that causes some issues. But on that note, we will call it a day. Take care.